Hello, everyone. A very warm welcome. Let me begin with a little story. Imagine you're standing at the railway station, suitcase in hand, but oh no, the lock on your suitcase has a number code. It has four wheels, each wheel showing digits from 0 to 9. You remember the first digit is 7, but the other three? Gone from memory. Now, will you sit there and spin those wheels endlessly, testing every possible sequence? That would take ages, right? Pause. Instead, mathematics comes to your rescue. By applying a simple principle, we can count exactly how many attempts you'd need without trying them all. And that's the gateway into the world of permutations and combinations, techniques that help us count arrangements and selections quickly and smartly. So, how does this work? Enter the fundamental principle of counting, also called the multiplication rule. Here's the idea. If one event can happen in m ways and the next event can happen in n ways, then together, the total possibilities equal m multiplied by n. Say it with me. Total equals m times n. Take it a step further. If there are three events, the total outcomes equal m times n times p. Simple multiplication. Think of choosing clothes. If you have 3 pants and 2 shirts, then for every pant you can pick any of the 2 shirts. That's 3 times 2 equals 6 different outfits. Multiplication saves you from writing down all the combinations. Isn't that neat? Let's look at a simple yet fun illustration of the counting rule. First, take Mohan. He has 3 pants and 2 shirts. For each pant, he can pair it with 2 shirts. That makes 3 multiplied by 2, which equals 6 total outfits. Now let's consider Sabnam. She has 2 bags, 3 tiffin boxes, and 2 water bottles. Step by step, first, she chooses a bag in 2 ways. For each bag, she can select a tiffin in 3 ways. That gives 2 times 3 equals 6. And for each of those 6, she can pick one of 2 bottles. Multiply again, 6 times 2 equals 12. Notice the sequence of selection, first bag, then tiffin, then bottle. At each stage, the available options multiply to give the overall count. That's exactly how the multiplication rule works in practice. Alright, now let's move from lunch boxes to language. Take the word rose. If we want to arrange all 4 letters without repetition, the first spot has 4 choices, the second has 3, the third has 2, and the last has 1. Multiply them, 4 factorial equals 24. But if repetition is allowed, oh boy, each spot can be filled in 4 ways, giving us 4 to the power 4, that is 256 arrangements. Or consider colored flags. Suppose you pick 2 out of 4 distinct flags and place them vertically. The top position can be filled in 4 ways and the bottom in 3 ways. That's 4 times 3 equals 12 signals. So whether it's words, numbers, or colorful flags, the same multiplication principle works like magic. Now, let's level up with a slightly bigger challenge. Imagine we have 5 distinct flags and we want to make signals by arranging at least 2 of them on a vertical staff. Case 1, with 2 flags, that's 5 times 4 equals 20 signals. Case 2, with 3 flags, it's 5 times 4 times 3 equals 60. Case 3, with 4 flags, we get 5 times 4 times 3 times 2 equals 120. And finally, using all 5 flags, 5 factorial equals 120 again. Now add them all, 20 plus 60 plus 120 plus 120 equals 320 total signals. It's like building Lego towers. You pick how many blocks you want and multiply your choices at each step. The more you add, the faster the numbers grow. Let's pause and reflect. Did you notice something? Sometimes the order of arrangement mattered, like with letters or codes. Other times the order didn't matter, like with handshakes or committees. When order matters, we are talking about permutations. When order doesn't matter, we are in the world of combinations. And underneath both lies the same foundation, the multiplication principle. Think of it as the roots of a tree from which branches of permutations and combinations grow. In the coming lessons, we'll climb up that tree branch by branch. So, to wrap it up, today we saw how mathematics can make counting effortless. From suitcase locks and school outfits to words, digits, and even colorful flags, the multiplication principle showed us the way. Instead of listing hundreds of options, we just multiplied choices step by step. This principle sets the stage for two powerful tools, permutations, where the order of arrangement is crucial, and combinations, where order is irrelevant. And that, my friends, is the exciting beginning of our journey into permutations and combinations. In the next session, we'll formally define permutations and derive the general formula. Trust me, you'll start seeing counting in a whole new light.